we have a new video, and this is all about half-life. So this is a very short module on what half-life is, the formula used to compute half-life, and some problems, and that would support the theory of half-life. So what is half-life? It's not the game, okay? I went to Google and checked. I was looking for images that I could put on this presentation. Unfortunately, what I saw were the game, the Half-Life game, which I'm not really familiar, but this is not the game, but this is actually a quantity in your nuclear chemistry topic that we really have to study. Okay, so what is half-life? Oops, there you go. I think there's another bullet there. First, it's the time required to consume half the reactant. So we know from our nuclear reactions that there are fission, there are fusion, there are different decays. So this is actually the time required to consume half of the reactant. Most of the time, we know that on the left side of the nuclear reaction, we have our reactant. On the right side will be our product. So this is half the reactant consumed in a given amount of time. Next would be half-life is the amount of time it takes for half of the atoms of an unstable isotope to decay. This is just a more detailed um, definition, but basically it's the same one as the first bullet. And of course, atoms with short half-lives is just something to note, are more unstable than those with longer half-lives. So the longer half-lives it offers, it's actually a more stable isotope. So let's consider one example. This is protactinium. If I'm not mistaken, this is protactinium. Let me just check my cheat sheet. This is protactinium, Pa. So it has a mass number of 233. So its half-life is 27 days. This means that 200 grams, for example, of a given Pa will decay according to the following table. This is not computing it yet. This is just using inspection method or common sense in determining how half-life works. For example, initially at the onset, day 0, so number of half-lives, none yet. So number of Pa remaining, that's 200 grams, because we started at 200 grams, so non-decayed yet. But after 27 days, because it says the half-life of Pa233 is 27 days, that will be the first half-life. You can see it from this table. Therefore, 100 grams has decayed, and the remaining from the original is just 100 grams. And then we'll take another 27 days. So that will be on day 54. So number of half-lives already consumed will be 2 half-lives. And of course, and then divide that again. What's remaining, you have to divide it again by 2. The concept of half-life is it always takes half of the original quantity or the original amount. So from 100 grams, this becomes 50 grams. And this decay now already is 150 grams. And then another 27 days or another half-life will be added to this table. So there are 3 half-lives already, which means, again, that will be diminished by half of the current life, which is 25 grams. So whatever is left is 25, and then decayed already is 175. And then on the 108th day, that will be the 4th half-life. The remaining P is just 12.5 grams, and what decayed is already 187.5, and so on. So this is how you analyze it, by just figuring out the diminishing factor of half the life. So this is using a table. But of course, by the way, before we go to the formula part, this are common half-lives of radioactive nuclides of radium. For example, radium-223, the half-life is 12 days, 224, 3.6 days, radium-225, 15 days, and so on. So, of course, we know that radium is one of the radioactive isotopes, so it actually has different half-lives depending on the mass number. So in formula form, this might look different from other formulas that you see. I find this the simplest of the different half-life equations that I've been using. This one is foolproof, meaning if I use this, I don't have to remember other formulas or use a certain quantity or constant right away. So I just remember this. So this is the formula that I've been using for half-life. So it says A equals A sub O times 1/2 T over T 1/2. So let's just get the different parts of that equation. So A here will be the remaining amount. For example, you begin to analyze the isotope at the onset. It has this amount of, let's say it has this amount. So eventually after it decays, the amount will be different. So that will be the remaining amount. A sub O will be the initial amount. And then 1/2 is just, that's part of the formula. And then it is raised to T over T 1/2, where T is the time wherein you're asked to compute the half-life, and T 1/2 will be the half-life. Okay, probably for us to understand this formula better, let's look at different examples. I prepared, let me see, 1, 2, 3, 4. I have 4 examples here. So let's just try to use that formula again. So let me just pull up my pen. Okay, let's go back to the formula. Okay, the formula is A equals A sub O raised to multiplied to 1/2 raised to T over T 1/2. Okay, pardon my handwriting. Okay, probably let's change in color so that it's clearer. Oh, sorry. Probably white. Okay. Now, as always, as we've been doing with the other videos, we are just really getting the quantities available at the start of the problem. So it says here we start with 1 gram of strontium 90. So I can assume that A sub O, that's initial substance or initial amount of the isotope, it's 1 gram. And then how much will remain after 5 years? So it means we don't have a remaining amount. And then we can say that after 5 years, that will be the amount of time. So we can say that's 5 years. And the half-life of strontium 90 is 28.8 years. Okay. So that's 28.8 years. So what do we do now? Well, just, basically, we can already compute for T. Or no, we're actually looking for A. I'm sorry. We're looking for A. So it's just really direct substitution of the values that we already obtained. So that is A equals AO. And then that's 1/2 T over T 1/2. Okay. Let me just get my calculator here. So you can go ahead, and if you want to like solve it while you're waiting for me to give you the final answer. So let's just substitute the values. So this is E equals AO is 1 gram. And then multiply to 1/2. And then T is 5 all over 28.8. And you do your, your magic in the calculator. What I'm going to do is I'm going to solve it with you. So that's 1 times, I don't even have to do that. It's just 1/2 raised, raised to 5 over 28.8. So the answer that I'm getting is 0.89. So as agreed, we'll be rounding off our answers to the nearest 2 decimal places. What I'm getting is 0.886. So I'll round it off to 0.89. And that will be in grams. Well, we can also analyze the answer that we're getting. In what way? We know that the half-life is 28.8 years, and we still just analyze at a 5-year period. So most probably it's not gonna decay like half right away because 5 is not very near 20.8. So that would probably decay in a longer time frame. Okay, this is the first example. Again, it's very simple to solve problems like this as long as you can identify the correct values for the different variables. Okay, let's have another one. Example 2, another isotope of cesium or cesium-137 has a half-life of 30 years. If a 1 milligram of cesium-137 disintegrates over a period of 90 years, how many milligrams of cesium-137 would remain? You can see from this example that it's just milligram, milligram. So actually no need to convert quantities. So all you have to do is again, get whatever is available in the problem already. I can see that, here you go, half-life is 30 years. And then it says 1 milligram of cesium. So we can see that at the onset, there was 1 milligram of cesium-137. And then we already have a given time. Time is 90 years. And what are we looking for? We're actually looking for how many milligrams of cesium-137 would remain. We're looking for the amount that would remain after this decays in this amount of time. So we go back again to our original formula. So that's A equals EO 1 half T 1 half. Okay. So we're looking for A. So substitute 1, and then that's 1 half, and then T, and that will be 90 over 30. A now is equal to, let me see, that is 1 half raised to 90. Let me just do that. 90 over 30. So I'm getting 0.125. So 0.125, and that is milligram. Quite simple, right? So that will be the amount that will be remaining in a period of 90 years if the given half-life of cesium-137 is 30 years. So you started with 1 milligram, and then you can actually do your table to double check your answer. If you feel that you have, for example, you're given more time, you want to do a tabular analysis, you can do so. Just to, do a check and balance of the values that you're getting. The next one, we'll have another one. So what I'm doing is actually just moving around the formula for half-life, wherein different parts of the formula are missing in the problem so that you can just practice your math skills as well. So for number 3, we have this one. It says here a 2.5 gram sample of an isotope of strontium-90 was formed in a 1960 explosion of an atomic bomb at Johnson Island in the Pacific test site. The half-life of strontium-90 is 28 years. And what are we looking for? In what year will only 0.625 grams of this strontium-90 remain? So let's get the different values that we see in the problem. 2.5 gram sample. That will be our AO. I have this. So that's A, because that's what remains after the decay. So 0.625 grams. We also have another, okay, here. The half-life of strontium-90 is 28 years. So T, 1 half of that isotope is 28 years. Excuse me. And what else? We're actually looking for in what year So we're looking for time, but it says here what year, because there is a start year, which is 1960. So that's a start year. Meaning when you say start year, this is where, or this is when the test was done. So again, let's look at our formula. So it's A equals, as you can see, I just would work with this formula, nothing more. Okay, so I'll probably have to isolate this. I'm looking for t, and it's in the exponent part of this right side. So I'll probably work with this. AO equals 1/2 t over t 1/2. And usually when we're given something like this, we get the natural logarithm. So ln of a, oops, sorry, a over AO is equal to t over t 1/2 ln of 1/2. Okay, that's actually breaking it. Remember, in the rules of logarithms and natural logarithms, if you take the natural logarithm of both sides, the exponent will become, we'll have to bring it down and retain the natural logarithm of whatever is left here. So we have to isolate t in this equation. So what do? We can say that, okay, t 1/2 times ln of a over AO all over ln of 1/2 is equal to t. And then we just have to plug in the values. So t is equal to t 1/2, it's 28, multiplied to ln of AEO. So that's 0.625 all over 2.5 all over ln of 1/2. And can I write here? I know I can't. So let's just put it here. What I'm getting is, hopefully this would derive the correct answer. That's 28 times ln of 0.625 over 2.5. So that's over ln of 0.5. So I'm getting 56. So t here is 56, and that is 56 years. 56 years hence. So we have to add it to 1960. So, but it only tells in what year. So 1960 plus 56. So just add that plus 56, 2016. So the answer here is, the answer, I'll just insert it here. The answer is 2016. Okay. I hope this is clear, and I hope, so no matter what, for example, you're given this example, but it has a different value for the initial amount, you can just always apply this solution. And by the way, you always have to round off nearest whole number. But in this case, what we're getting were exact numbers, so no need to really do a big deal on the rounding off. Okay, last example. Hopefully, let's just go back to the different problems. First one, getting the remaining amount. The second, also remaining amount. Third one, we'll be looking for what year, because there's a start year. What we did was get the time for the decay. And for my last example, let's have one. After 60 days, 10 grams of radioactive isotope remains from an original 40-gram sample. What is the half-life in days of this element? So 60 days, so that is T, 60 days. And then we have 10 grams from an original 40 grams. So AO here is 40 grams. A is 10 grams. So what are we looking for? We're looking for T 1/2. You can actually just go back here and derive an equation. As you can see here, we can use this one. If you're very familiar with the formula already, you can just move around and use it. So let's bring that. As we said, we can say that the natural logarithm of AO, right, is equal to, let's go back, let's check, T1/2 over T1/2 times ln of 1/2, right? See? So from this formula, you can already get T1/2. So let's just work with it. So this is ln A over AO over ln of 1/2 is equal to T over T1/2. And I would need T1/2. Therefore, T1/2 is equal to T times ln 1/2 all over ln A all over AO. So T1/2 now is equal to, what is T? T is 60 multiplied to ln of 1/2 all over ln of AAO. So that will be 10 over 40. So hopefully we get an answer here. So this is T1/2 is equal to, I haven't solved them, but I just know the answers. I just want to validate as well. So that's 60 times ln of 0.5 all over the natural logarithm of 10 over 40. Okay. So I'm getting 30. So the half-life of this radioactive isotope is 30 days. Okay. So there you go. I will stop at this for this video. So there will be another video for a different set of problems. But hopefully for the 4 examples that are in this video, you already get a grasp on how to solve half-life problems. Okay. So I'm really, really happy that I get to do these videos again. I know you missed them. I miss doing them too. So until the next video, thank you so much. Don't forget to share and subscribe to the channel. You can share it with your friends, your classmates, your blockmates, or whatever. Just please continue supporting the channel, and I'm going to forward in making the videos better and more, and we'll be giving you more information regarding the different topics we have for chemistry. Okay, thank you so much. Have a good day and keep safe, everyone. Thank you. Bye bye.